Okay, welcome everyone for the unusual location of our X colloquium, but it's actually a fitting location for Krysta, because I remember when I was at Microsoft and we had some group who had mathematicians who actually wanted to build quantum bits, and Krysta said, no, wait a second. If you have a quantum computer, you need algorithms. So she's actually one of us here at the Simons, or at least was at some point. By now, she heads all of quantum at Microsoft and is deeply involved in actually building qubits. She is a technical fellow, which is sort of the highest research thing you could be at Microsoft. Now is VP. She is member of many societies, AAAS, or the American Academy of, is that the one in Boston, or the
APS and
AAAS, which one? There are two AAASs.
And science one.
The science ones, the American Physical Society, the Society of the State of Washington, and she has over 30 patents and over 70 publications. I don't want to detract too much from her. It's a real pleasure to have you here. I haven't seen you for 5 years since I'm at Berkeley, so it's wonderful to have you as our guest. She will tell us on why quantum and how you actually should do qubits.
Thanks, Christian. Well, thank you, everyone. I'm sure there's a whole variety of backgrounds in the audience, so I tried to tailor this to hit a few different flavors. As Christian mentioned, I started at Microsoft actually 19 years ago, and I had been working in quantum computing. I had studied quantum algorithms and quantum error correction, but what really was my passion was figuring out how can you program these things and build them, right? How would you take an algorithm? I always remember learning in college. I had a course from Andrew Wiles on cryptography, and he, in that course I learned about Shor's algorithm, right? This quantum algorithm that could break our mainstay of e-commerce today. Of course, e-commerce wasn't really what it was now at that time. But I remember learning that and thinking, gosh, this model of computation is fascinating, but how would you actually translate that down to the hardware, right? What does that hardware look like? What does it do? And how would you map it down to that in an efficient manner? So I really thought a lot about programming, the programming stack, the software stack, right? Translating algorithms all the way down to physical instructions. And of course, in quantum computing, there's some pieces that are a lot more challenging and fun, right? In particular, error correction, right? Quantum computers are very noisy. That's something we don't really worry about classically, right? I mean, heck, you can drop your phone and nothing really happens to it. You might break your screen, but it probably still computes. And that's not the case here. So I hope today to shed light on, kind of different facets, different layers here in the stack, and where we are in quantum computing, where those machines are at, and where we want to be. So, why quantum, why now? And we'll talk a little bit about a combination of data and qubits. So when I first joined Microsoft, I actually switched. I worked on machine learning for a while I kept kind of my toe in quantum computing. And what I learned in that experience is, it's all about data. And I think this statement can't be more true today. Data is everything, right? When I'm sure you're all using ChatGPT or hopefully Copilot, but it's all about data. It's taking your data, it's training on that data, it's grabbing data from all sorts of sources. So it's really all about data. And the thing is no matter the model you build or the technology you build, I like this quote, right? Data is the precious thing. Right? Data carries on longer than the system itself, right? So when we think about transforming what we know, how we can predict and prescribe new solutions, right? It's all building on data right now. And that's true even when we look at Nobel Prizes from last year. where you had the Nobel Prize in physics going to essentially machine learning, the Nobel Prize in chemistry essentially going to AI, right? Again, all about data at the core. And I feel like I have to mention the Nobel Prize from this year, which took place on this very campus, the extraction of data from these experiments that really drove a deeper understanding of quantum mechanics and the tunneling mechanism there. But our world is driven by data. And what I learned in my early years at Microsoft, we did quite a bit of work on information retrieval and how to build essentially web search, right, using data. And I mention this here because the data, what did we learn? We learned obviously more data is better, and we see that right now, right? The explosion of data, the ability to just train models on vast amounts of data has completely changed the trajectory of solutions, right? We also learned, though, that if you have just a little bit of high quality data, that also can make a really big difference. And it's not always, I would say that was non-obvious at the time. I think now we kind of take it for granted, but some of these results are, from quite some time ago. But, just a little bit of really good data can help you, for example, learn and model things in kind of a subfield, or say like a different language or a different domain in a much better way. And in addition, feeding just lots of data and lots of signal makes a huge difference. So we all know this, now very, very much, especially, in the world of LLMs. But why am I mentioning this in the context of a quantum computing talk, right? You're probably wondering, what is she doing? She seems on a tangent. But this is highly related. Because what do we want, what do we see? Right now, what's setting the bar? In science, in new solutions, right? It's using different AI or machine learning models, right, to really set a new bar in terms of what you can solve, what you can infer, what you can model. And of course, we want these, the inference to be very fast. And on a classical computer, that's true, right? Inference is fast. But how do I, now that sets a new bar for quantum computers. We don't just get to produce a solution with a quantum computer anymore, right? We have to also compete, if you will, right? We have to compete with what AI models can do, right? So the bar it's going up, right? AI models are very, very powerful, or ML models, right? Very, very powerful, and it's setting a new bar for science. And what we've often, really seen our quantum computers as is an opportunity to solve new problems in science, right? Areas, for example, calculating solutions in chemistry and material science in particular. We've seen quantum computers as well paired to that domain. But now the bar is pretty high with AI. And so what should we do? What should we do instead? We should think about quantum computers as augmenting the era of AI, right, as being an additional capability that augments what we do in AI. And how might we augment it? Well, we've done, throughout the field, right, there's been a lot of work looking at quantum machine learning, but it turns out actually doing that training and inference on the quantum computer itself, it's quite expensive if you have to load classical data, right? That's not what we want to do. We need to use the quantum computer in a different way. And so we've started to think about the quantum computer as a data generator. It's not to say it won't be a solver, right? Obviously, to generate data, you're also solving some problem to get that data. But if you start to think about it as a way to get data efficiently that you can't otherwise get efficiently on this planet, it kind of unlocks a new, not only a new architecture, right? You need to think about how do you infuse that data into the AI models today? How much data do you need? Going back to my comment on small amounts of high quality data. What does high quality mean? How high quality and how much of it do I need from the quantum computer? And these are still not known. We don't know the solutions to this at this point. But these are the types of problems that I think in the coming couple years in particular merit a lot of study. Right? How do we get interesting, high quality, and the right amount of data from quantum computers? And especially, is it possible to get that from small quantum computers that aren't yet scaled to 1 million qubits? And what will that do for different areas of, say, learning, training in science? So that's what we want to do with our quantum computer now, is think about it as a data generator. And part of that motivation is that we can go and solve a problem on a quantum computer. For example, if we want to do quantum problems in quantum chemistry, right? You can look here, the different methods here on the x-axis, right? Think of that as the amount of accuracy you need in your solution, and the y-axis is the cost of getting that solution. So you could think of it as the complexity or the runtime, right? So in terms of methods in computational chemistry, right? There are many different methods in computational chemistry plotted on this green line that more and more accuracy, you pay the price, right? They're more expensive. Exponential in runtime, for example, also then exponential in cost, right? So some of these are going to be just completely intractable, right, in terms of using them for practical problems. But with quantum, we can actually lower the cost, right? There's quantum algorithms for Hamiltonian simulation that one can use then for computational chemistry, and we can lower that cost. But it still doesn't lower it to the level where it's much, much less expensive. But what we think is that instead, if we do the right, if we have some calculations and data coming from the quantum computer, we can lower that cost even more. And so this is the promise, and this is what we need to prove out in the coming couple years as we have quantum computers that can produce data to power these kinds of models. All right, so if I want to do that with my quantum computer, though, I need qubits, right? I need a quantum computer, and it needs to be of a size that enables me to produce such data, which behind that means solve instances of that problem in an efficient amount of time and giving me an accuracy that's good enough. So the thing is, right, the catch, as you all know, is that that data that's coming out of the quantum computer, it's only going to be as good as that quantum computer can be. It's going to be limited to the size of the quantum computer in terms of what kind of data I can get out. And of course, those qubits, when I say as good as the qubits, I mean as good as the qubits and their operations, right? And so what's the issue? Quantum computers are noisy, right? I like to think about it like this. You get a spinning top, say a qubit is the spinning top, and now you get to try to keep 1,000 or 1,000,000 of them spinning all at the same time for a month. Because some of these problems are going to take a month to solve even on a quantum computer. In fact, they can take much, much longer, but we probably don't wait more than a month. And so this is a really hard problem, right? And I think it's a good visual for just how hard it is, right, to keep all of these qubits and their operations fault-free for a month. That's hard. So what can we do to help, right? The reality is we have to build a machine from noisy parts. And when we say noisy parts, what does that mean, right? So for a reliable quantum computer, we need to get, our algorithms require things that are upwards of, say, upwards of 1 billion operations. And those operations have to occur without fault. And where are we today? If we look at quantum computers today, we'll call them, to use John Preskel's term, noisy intermediate scale quantum computers, so NISQ machines, right? NISQ machines are roughly, okay, you can add a 0, subtract a 0 here, but roughly they're around, you can apply roughly 1,000 operations without fault. All right, so that's a very small, when you think of the world of algorithms, right? Especially compared to the classical algorithms we're running all the time, right? That is a very small number of operations. And we need to get to algorithms that require more operations, upwards of 1 billion. And of course, right, there's stepping stones to get there. Obviously get to 1,000, 10,000, 1 million, right, 10 million, et cetera, right? So we need to grow the number of operations that we can run on our quantum computer. And really, this is what it means to be reliable, right? We're building a quantum computer not just to hold qubits in memory, but to compute. So what's really important to track is how many operations are we able to compute to run, to use on the quantum computer and still get a reliable result. So I like to think of everything in terms of a computation, right? Not just holding qubits in memory. So we have the NISQ machines, and I like this quote from John Preskill, that there's no proposed applications of NISQ computing with commercial value, and there's no persuasive theoretical arguments indicating that commercially viable applications will be found that do not use quantum error correcting codes and fault tolerance. I think most people in the industry now believe we have to have quantum error correction and fault tolerance to power the quantum computer and make it reliable enough to do commercially valuable calculations. And so quantum error correction is absolutely critical. And for those of you who don't know about quantum error correction, right, what is just the gist of the idea? We have our physical hardware, right? I like to think of this as taking noisy parts. We get lots of noisy parts, and we get to try to make something that actually works from the noisy parts. So the physical hardware has some failure rate that's plotted on the x-axis. And from those noisy parts, we want to get something that operates in a better manner than the noisy parts themselves. All right, so on the y-axis, we call it the logical failure rate. So this is what I get by using those noisy parts in a special way, orchestrated way. I want a lower failure rate of the machine, right, of what we call logical qubits, right? So the idea then is, if you take some setting on the x-axis, right, I want to be lower than this dashed line. That means if I took noisy parts that operated at 10 to the minus 3, if I'm in this blue region, I'm now operating in a better regime, right, with a better error rate, a lower error rate, than I was using the physical qubit directly. So using noisy physical qubits, choose your point on this axis based on your hardware. I use error correction to get something that's in the blue region. Now, what do I really want? And that means logical qubits.
Boundary just an illustration, or do we know that somewhere theoretically, if you have 10 to the minus 2 errors, you just can't do one?
Yeah, in this plot, this is just an illustration. However, it is indicative, right, for a given code, for a given quantum error correction code, right, and decoder, in fact, there's a threshold at which if my parts are noisier than that value, error correction hurts you instead of helps you. And so you calculate this threshold for a given code and decoding capability. And then you have to make sure you're below that threshold value for it to work at all, right? So you can't have parts that are so noisy, right? Then the noise just accumulates faster than you can correct it. Right. But indeed, most codes, right, they tend to have something that looks like 1%, 3% threshold, something like this. Yeah. And some thresholds are worse. All right, so the name of the game then, what we want to do for, with error correction is we want to actually find error correcting codes and decoders, right? Ways to outpace the noise and fix it. And we want to do it such that actually we want to relax the hardware constraint, right? We actually want to relax what the physicists and experimentalists and builders have to go do. So, ideally you're somewhere over here, but hardware designers are going to have to try to push left, right? And as they push left, error correction becomes easier. It becomes less costly. And at the same time, we want to design codes, right, that if you choose a given point for the hardware, right, my hardware operates here, for example, I get as low of a logical error rate as possible for that code. So this is part of the fun in designing codes, right? You take a look at what the hardware constraints are, and you try to design a code that is far, going down and left as much as possible, but goes, for a given hardware setting, goes down, right, as much as you can on that line, right? So you really want to travel down a given physical hardware line. And then in addition, right, with error correction, what we have to do is we have to apply it all the time, right, at some regular cycle time. Because ultimately what we want is, right, errors accumulate, and then we want to make sure we're removing them out of the system, accumulate, remove, right? So when we think about fault-tolerant computation on a quantum computer, you know, you're doing these logical cycles all the time, right? And we call it syndrome extraction. We're constantly probing, right? I think of it as detect, correct, compute, right? We're constantly detecting what's happened in the system by looking at noise, by looking at signals, right, of the noise. We call them syndromes. We correct that using a classical decoder, an algorithm that's looking over those bits and inferring where the problems were. And then we correct it and we continue our computation. And we need to do this all the time. Okay? All right, so how does this work in practice then, right? So we take quantum error correction and we need to actually make hardware that works. And the beauty right now is that hardware has come along where, you know, you can look at the different qubit numbers on this slide, right? Quantum hardware has advanced such that we don't just have 5 qubits or 10 qubits, right? IBM and Google, they're up well, you know, over 100 qubits. Quantinuum, you have a 56 qubit chip. They're about to release their 96 qubit chip. Neutrals, you have 256 qubits and you know, or roughly in our work with atom computing, we have 256 qubit chip, and we're building for a 1200 qubit chip right now. So you have a lot of, you know, you have handfuls of qubits that you get to take advantage of. So this is very exciting. Now they have different properties, right? And so on superconducting qubits, what's some of the, you know, there's always like a set of pros and a set of challenges, right? Superconducting qubits, very fast, right? Fast operations. But arguably, you know, you're at 100 qubits, not 250 to 1,000 qubits, right? So the number of qubits is more constrained right now, growing, but at this time, right, steadily growing. Trapped ions, lower qubit count, but they have very, very high fidelity, right? Their entangling operation has some of the lowest error rates in the industry, right? So they can operate that 2-qubit operation at 99.9% fidelity. In addition, they have a simulated full connectivity, right? So in the ion trap system, the ions, which represent the qubits, they move. In this design, they move around this racetrack. And where these blue squares are is where you can bring them together to interact and entangle. So your 2-qubit operation can occur in parallel in these zones. But you need to move to the zone. All right? But you get to shuttle around and move to the zone, shuttle around, move to the zone, right? So you get all-to-all connectivity, but of course it comes at a price, and the price is time. It takes time to move around and go in, right? Neutral atoms, similar idea, also simulated all-to-all connectivity. So you get full connectivity, but same thing, you need to move. And in the case of neutrals, you move to a zone, right? So you'll have a row or a series of rows where you move the neutral atoms up. Each neutral atom is a qubit. I get to lift and place up and back, up and back. But again, to get that connectivity, I pay the price of time. Paying the price of time, by the way, means I pay a price in noise. Right? Often time means my qubits are also degrading during that time. And so I have that to handle, right? I need to overcome that. But the beauty of neutrals, for example, large qubit count. So right now we are building a system with 1,200 qubits with atom computing. But let's focus here. And then I guess on you know, both atoms and ions are slower than superconducting qubits. But you get more connectivity. So you're playing a game, right? You really want to co-design and custom design codes for each of these architectures, right? Because they have different pros and cons. And so when we think about that, right, when we think about quantum error correction, I think many of you probably have heard of the service code, right, which is this kind of a more standard way now. It's very well known. But the service code, you know, the beauty of the service code is for an architecture where your qubits don't move. You know, it's a great path, it's a great method, to perform quantum error correction, right? In contrast, if my qubits move, I can change the graph, right? I can consider different codes. I can consider where that underlying graph actually has long-distance connectivity requirements, which in a certain architecture, I get to move my qubits. That means I have access to this graph very easily. So in a superconducting qubit architecture, this graph can be much harder unless you have long-distance couplers, right? But in an ion trap atom architecture, this is much more accessible. Now, why would I make this change? Because these codes can have less overhead, right? Ultimately, quantum error correction requires more qubits and time. So I want to walk you through some of what we've done in the last kind of year and a half in actually showing quantum error correction can work. And it can work in hardware. And it works very well in hardware, especially when you co-design with the hardware itself, right? So you co-design the code and the hardware. So the first set of results I'd like to walk through is work that we did with Quantinuum. So Quantinuum has a range of processors, right? A range of chips, everything from what's called H1 that had 20 qubits, 20 ions. Each ion is a qubit. Also H2 device, they have 2 systems on H2. It had 32. They've upgraded it more recently to 56. We've operated on all 3 of these designs. And then, as I mentioned, they're about to come out with a 96-qubit chip called Helios. Their gate errors are, very low, right? These are the lowest, really some of the lowest in the industry, at around, right around 10 to the minus 3. So very good 2-qubit operations. Now, when we started on this work, right, we considered 2 codes. We developed 2 codes that really were developed with Quantinuum hardware in mind. And now these codes actually can operate in other hardware settings as well, like other architectures. But when we designed them, we were really thinking about that ion trap architecture, where you have movement, you have some number of zones where you get to do 2-qubit gates in parallel, and then, of course, taking the noise profile of the machine. Good 2-qubit gates, but it takes time to move, time to enable that parallelism, and so we have to account for that. And I think what's fun is, in the world of quantum computing right now, there was a lot of research done in quantum error correction, 20-some years ago. Really, really great work that now we're actually going back and rereading and understanding, wow, there's ideas in here that could work today, now that we have multiple architectures on the table with enough qubits. These things start to actually make sense and can be done in practice, right? And so we were very much, the carbon code we invented was very much inspired by Manny Nill's work from 2004. And this is the best paper I know of that gives a very high threshold, right, to the question of threshold. He shows that even if you had errors of something like 3% per gate, error correction can work. Okay, but there was a catch in this, right? Error correction could work, but it would be very costly. This paper uses a lot of qubits and overhead, but it shows it could work, right? So your qubits and your operations don't have to be so good, good enough, but error correction could work. And so we took that, and in particular, Adam Patznick took that work and that code and started to bring it down and bring it down and bring it down, and I'll show you just how far down it got. Originally thinking it would require something like 200 plus qubits to show an error-corrected patch in a logical qubit, but getting it way, way down and showing it in something like less than 20 qubits. So I'll show you that work in just a minute. The other code was also inspired by earlier block codes and code constructions. And here what we did is took a code and realized that we could, and this code you can view geometrically, for example, on this graph where the qubits sit on the vertices, the stabilizers are on the cubes, and the logical operations are on the faces. And we could take this code and actually have it be a better code for working in practice by actually not using 2 of the logical qubits, right? So this code also, it's a block code where you have originally 6 logical qubits in 15 physical qubits, right? So error correction is all about taking a pool of physical qubits, encoding them, and then having logical qubits that operate better than the physical qubits. And so here, 16 physical qubits, 6 logical qubits, and distance 4, that tells me about my error correction properties. We were able to get rid of 2 logical qubits and still have a nice distance, but what that does is makes it more practical, reducing the weight of the stabilizers of the code. So we were able to take this code and really have it be more performant for the ion trap architecture. So what does this look like in practice, just to bring it to life? If we take the surface code, right, this is an example for that on the Willow chip, right, at Google, they've used the surface code, they've demonstrated around 1% error per error correction round. 1 logical qubit, so that's the qubit you would use at your algorithm level, is encoded in all of these physical qubits. Okay, so that's how the surface code looks, roughly. So you use that many physical qubits to represent your logical qubit, and they get around 1% error per error correction round. Now with Quantinuum, we took this carbon code, as I mentioned, inspired by NIL, and in this many qubits, we got not only 1 logical qubit, we get 4 logical qubits, right? So we use a code that's 1224, and we can get 4 logical qubits, and we get a much better error. And again, remember, Quantinuum has some of the best 2-qubit gates in the industry. And similar, we can take the tesseract code, and we can get 12 logical qubits, with each logical qubit requiring just this many physical qubits. And so you can see when you start to co-design the architecture and the code, you can get much more efficient codes, right? You can get many more logical qubits for fewer physical qubits, while still getting much better error rates on those logical qubits. And to give you an idea of what, for example, the carbon code looks like in a little more detail, for the carbon code that we ran on Quantinuum, we were able to perform, and this is, I think this is arguably the first time logical qubits were demonstrated to outperform physical qubits, and to do that in many rounds of error correction. So this is really the first demonstration that error correction can work when applied, over many, many rounds, right? And so we ran many rounds of error correction, and we compared it to different physical baselines on those physical qubits, where you're running, say, C0s on the physical qubits. And on the error correction side, we're doing rounds of error correction. And you can see in blue and orange are 2 different physical baselines. Error rate is the y-axis. So as you go out on number of rounds, you can see as we do more and more rounds of error correction, we're getting a significant improvement by using logical qubits as compared to physical ones. And the same thing, on the right-hand plot, you can see that by using error correction, we get a significant reduction in the error rate per round. So this was a huge indicator that quantum error correction can work. Now, it's not enough just to do error correction, right? We don't want to just error correct a memory. We also want to make sure that we have logical qubits that can perform a computation, because ultimately we're building a quantum computer. And so the other thing we did with Quantinuum is we took a circuit, right, a logical computation, for example, this computation here. This looks very simple at some level, but never had it been done in practice where a fault-tolerant computation was performed that really required error correction to succeed. And so we took this computation, and we used the tesseract code. And again, in the tesseract code, from 16 physical qubits, we get 4 logical qubits. So we can run this computation here, 4 logical qubits, and 2 ancilla qubits are required. So 18 physical qubits, we can run this fault-tolerant error correction procedure. And what we do is we take that circuit, and why do we need error correction? Because a single fault can actually propagate and spread to a logical error. So we need to make sure we can correct against that. So we add error correction in between the different layers of compute. And what we find is that when we use logical qubits instead of just physical qubits for the computation, So now each of these lines, right, circuit diagrams are read left to right. Each of these is a logical qubit now. We compare to each of these being a physical qubit and run the computation. And we see what happens. And the physical circuit at output has an error rate that's 2.3%, whereas the logical qubits come out at 0.2%. So the logical qubits are better than the physical qubits in this fault-tolerant computation. And this is the first time, again, that fault-tolerant error correction was required for a computation, and we see that it can perform better. So a great indicator that error correction can work. And of course, we did this in our paper. We have many, many different examples where we can show that, again, we get improvements consistently across the board on different computations. In this case, we're performing computation to prepare different entangled states. And we can find that the logical qubits consistently outperform the physical qubits. Now, on the atom computing architecture, I want to switch gears to the other hardware. With atom computing, we can do similar things. And so here in the atom computing system, you have a register of atoms. Now, each of these represents an atom. Each atom is a qubit. And what's a bonus here? Atoms are all the same, right? Atoms are identical. So each of these atoms should be identical. And what you do is you load atoms into a register, and you get to design, in fact, what the register looks like. So when you know your code, you can design how this layout looks. And so again, a big opportunity for co-design to make logical qubits operate in a more efficient manner and help scale up. So 256 qubits, and what happens is you need to move atoms. So you have highways in between that the atoms can enter the highway and move. And you're going to move to a zone that sits at the top and enables the 2-qubit operations and entangling operations. How do these things move? They move with optical tweezer. So you literally pick them up with a tweezer and move them, a light-based tweezer. And single qubit gates can happen in parallel in a given row. And then 2-qubit operations, as I mentioned, you move the atoms up, and then they go to this interaction zone, where then you can apply 2-qubit operations in parallel. So you can see in this architecture and the Quantinuum architecture, there are a lot of opportunities for optimization, right? Scheduling, routing, optimizing the movement. How do you, and you have constraints, right? It's not arbitrary movement here. You get a cross AOD, and you have to follow the rules of how the cross AOD works for picking up and moving atoms, right? How many you can move at a time, how rigid of a motion it has to be, et cetera. So ample opportunity to really co-design the system with the error correcting code you want to apply. And then ultimately, right, when you run it, you load your atoms up. You apply your circuit that includes movement. So here, this diagram, this is where the interaction happens. Here's the register. These lines show the movement. So you load up the atoms, run the circuit, and then you measure. Now, what's cool about neutral atom architectures is measuring is taking a picture, and these atoms fluoresce. And depending if they're in the 0 state or the 1 state, or if they have been lost, so atoms can fly away out of their optical lattice, and you get that information. So another bonus about the neutral atom architectures is you get additional information, additional signal about loss, right? So if the atom has disappeared during the computation or it disappeared upon load, you actually get that as a different bit, right? You get 0 or 1 or lost, and you can take that into account. And this is a real image of atoms, right? So you load them up, take a picture and see if they're all there, keep loading if they're not, apply the circuit, and then every time you measure, you get this extra signal about whether or not atoms have been lost. In addition, just a pointer to a more recent piece of work that atom computing did, showing that they can actually also do mid-circuit measurement. So you also have a zone for measurement where you move the atoms in, and you can actually then use mid-circuit measurement throughout the computation to perform error correction as well. And then you can reload during the computation. right? So new work there from June from Atom Computing showing that's now integrated in this architecture as well. And so what do we do in this Atom Computing system? What we can show is the largest encoded, at the time, the largest encoded cat state in the industry. And we could show that, for example, right, if you want to create a cat state, an entangled state, this is what you require at the physical level. But this, once you encode it, looks more like this, right? You can see that error correction has a cost, right? It's a lot of extra qubits and it's a lot of extra operations. So you're going from 23 controlled knot operations to something that has over 100 controlled Z operations, so entangling operations. So that's a big blow up, and it's asking a lot of the hardware. So, at some level, one could step back and say, it's amazing this works at all, right? But the key, if you're below threshold, you're really understanding the noise in your device, error correction can indeed work. That's such a huge deal. Can't emphasize it enough. And then, as I mentioned, we also can design the circuit so that errors, and we can have what we call erasure conversion. So we can convert errors to atom loss, and then we actually get atom loss heralded, right? We know when atoms are lost from the measurement. So that also can help with the codes. And then, of course, you have to schedule it. Again, a really important optimization problem for these architectures, especially as they scale up, is learning how to schedule the movement, how to lay out the architecture to make it as efficient as possible. So what we've been able to show is the largest encoded cat state. So this is a plot from Mario Kren, maintains a chart of the largest cat states ever produced. Now, all of these cat states are physical qubits, right? You take the physical qubits and you just do the circuit I showed you to create a cat state. But what we want to do is create encoded cat states, right? We want to do this with logical qubits. And the great news is for neutral atoms, we can create a 24 qubit encoded cat state, right? The largest physical at the time was 40. And so it's pretty big, right? Pretty big that we can get an encoded cat state for the neutral atom architecture. And in terms of beating the physical baseline, when we do a physical cat state, the unencoded physical cat state, you can see the error rate here on this gray bar. And then when we do an encoded cat state where we take into account that loss and error detection, you can see that we can greatly reduce the error on that cat state. So logical qubits work. Now I want to mention another problem that we did with the neutral atom architecture with atom computing in honor of Umesh, which is the Bernstein-Vazirani problem. So here the goal is to learn this secret string S, right? And then you have some black box, right? We implement the black box. It's essentially just controlled knot operations. And the point is, in quantum computing, we can do this with one query to the black box. Now, we want to do this and compare if we run this algorithm, if we run it with physical qubits versus logical qubits, right? Using a code, how do the results compare, right? So the Oracle implementation is basically just a string of C0 gates based on the string S. So we fix that with the number of C0 gates, and then we can run this computation. So we run this algorithm, again, on the physical qubits. The physical circuit looks like this, right? It's a sequence of controlled NOT gates that implement that Oracle. And then ultimately we encode. In this case, we used the 412 code, so it's an error detection code. But we're doing some loss correction. So we can take this encoding, the circuit blows up, as you can see, going from 27 controlled NOT gates to something that has over 164 controlled Z gates. So again, squinting, you say, gosh, why should this perform better than that, knowing that the hardware is noisy? Right? I think it's pretty incredible. Again, error correction works. And on top of that, it's not just that circuit we get to move all the time. right? So we also have to schedule and optimize the movement of those atoms to do those 164 2-qubit gates. Because remember, we have to move up to the interaction zone, move back, move up, move back, move up. OK, so we also have to schedule that. So you're adding all this onto that circuitry. So we optimize for that movement, and we run the Bernstein-Vazirani algorithm. This is a plot that is just the history of Bernstein-Vazirani implementations, right? So at the physical level, this algorithm has been performed on trapped ions, superconducting qubits, and you can see in some cases with very little, a smaller percentage of success. And we can run ours. And on encoded qubits, right? It's the first ever encoded version of the algorithm. We can run a string length of 27, so that's a 28 logical qubit circuit. And the unencoded success rate is 70%, but the encoded rate is 81%. So logical qubits work better. And we can see this for different string lengths consistently. So again, I just think it's amazing, something that much more complex works, right? The mathematics behind it work. As we increase the string length here of the secret string that we're hiding, we can plot the physical qubit version versus the encoded version, and we can see that consistently the error rate of the logical qubit circuit is consistently lower than the physical qubit circuit. So again, a huge win for error correction in logical qubits, going from something at string length 27 from 17.5% acceptance rate, of course, though, down to 8.6% acceptance. So we do have some acceptance rate differences. Now, also on the neutral atom machine with atom computing, we've done other results. You can look at our paper for that. We've done repeated loss correction and error detection. We also ran a number of different Bacon-Shor codes at different distances with different rounds of error correction. We also ran random logical circuits. And so as you can see, right, just the era of logical qubits is here. And that's really exciting because it means our machines are getting more and more reliable, right? So we have entered the era of reliable quantum computing, and really it's been quite a journey already. I like to think of 2024 as the year of the logical qubit. Of course, there are other groups also looking at logical qubits, but here with Quantinuum, we started with 4 logical qubits, demonstrating that in their early H2 device. We showed they were better than the physical qubits. We then tripled that number just in a matter of months. And again, with the Tesseract code, showed they were better than the physical qubits. And we used it in a fault-tolerant computation with repeated error correction. We then showed 28 logical qubit computation with the neutral atom machine from atom computing. And as I mentioned, we're now on the path to building a 50 logical qubit machine based on a neutral atom machine from atom computing that has 1,200 physical qubits. And so when we look at that progression, this is just music to my ears to see that we are progressing to the point where when you're upwards of 50 logical qubits with enough logical operations, you're in a regime where you can compute things you cannot compute classically. And the promise then for new solutions in science, new types of data, as I started with, is big. But we can't stop at 50 logical qubits, right? As I said, we have to get out to billions of operations and more, right? And those have to be reliable. So we have to continue to scale up. So I want to mention just a few results that along the lines of scaling up. We need more qubits. We need more compute, right? And that enables you to do larger instances of problems, right? So we need to co-design for even more logical qubits, right? The results I've shown, we've talked about, tens of logical qubits. We want to get to 50, 100, and more. And the way we've been thinking about it is taking logical qubit patches. So again, in quantum error correction, you have NKD. This is the number of physical qubits. K is the number of logical qubits. D is your error correction capability. You can correct D over 2 faults. So you want to really grow D, but as you grow D, typically, N also grows, and you may get outside the size of your machine. So it's really about co-designing with the machine constraints you have, and trying to get a high rate code, right, where you're using very few physical qubits per logical qubit. You want to really lower that logical failure rate, as we talked about earlier. That means I need a high code distance, but I also need a decoder that works super well for that code and the type of noise I have in my hardware. And that needs to be customized. And that's a classical algorithm, of course. And it needs to be fast. I need to be able to do it in real time on that machine, or with the quantum computer. So I need fast implementations of decoders. I need to make sure I have a very efficient logical cycle. So what happens, I'm always doing the syndrome extraction and quantum error correction. And that has some time, right? It requires some amount of time. I need to compress the heck out of that. Because as that grows, right, that means my logical operation times grow. And ultimately, right, the difference of 4 milliseconds or 400 milliseconds, that can make or break your ability to have that algorithm run. So you really want to look at the logical cycle. And then you also need to make sure that your code comes with operations, right? And this is something maybe sometimes we take for granted, right? It seems obvious that when you use error correction, you should be able to do logical operations and protect them. But it's not always easy to find efficient ones. And so that's something we need to do. So recently we put out a paper looking at all of this. We call it these are 4-dimensional topological codes. We call them, our nickname for them is called Beryllium. And so this family of Beryllium codes, it offers 6 logical qubits per patch. So it's a family of codes, in fact, that really is designed to hit all of these points. High rate, really good logical error rate, efficient logical operations, the ability to synthesize them. And the idea really comes from looking at the surface code as well, the 2D toric code, taking the toric code and rotating it and realizing as I rotate that code, I can get away with fewer physical qubits. So it turns out if this square was looking like a square instead of a diamond, my code parameters for the 2D toric code, the number of physical qubits is 2d squared for 2 logicals. But when I rotate that code, literally rotate how I encode it, I can go to d squared, right? So I can get away with half the number of qubits just by rotating how I interpret the code. And we can do this in higher dimensions as well, and that's the key. So we do it in a higher dimension, in 4 dimensions, and we chose 4 dimensions for a reason. It turns out that the 4D loop-only toric code is a single shot. It's the lowest dimension you can have for a single shot code. So what does single shot mean? It means I don't have to do D rounds, right, my distance. Typically in the surface code, for example, although this is for different implementations, people are looking at something called algorithmic fault tolerance. But traditionally, we've thought of the surface code as requiring D rounds of syndrome extraction to properly decode that code. Single shot means I don't have to do D rounds, right? That scales with the distance. I can just do some small constant, maybe just 1. And so why does that matter? If I have to do D rounds, I multiplied my logical cycle time by D. Right? Ultimately, D needs to be large to scale, right? I need something that's like D equals 10, 15, right? So that means I'm 10 times longer in my compute. So I want to compress that. Single shot matters, and this code has that. And then it also has a family. I just extracted some members of the family, some instances of the family. So we can find different NKD. K is always 6 in these codes. But we can find different instances of the family for different distances. And we get a substantial savings, up to 6x savings in qubits over the 2D toric code.
You build 40 qubit lattice in our world.
Yeah, so the beauty is, why did I design this? Why did we look at 4 dimensions here, and how do we build it? It's really the fact that we have all-to-all connectivity in our chip. So we don't have to, we do optimize the layout, right? That's where I was saying, like, we look at that, how we lay out the qubits, the physical qubits in the registers and in patches, right? So we lay them out in a way that we can maximize parallelism for syndrome extraction. We look at that movement, the number of cross AODs, and we optimize for that. But then the 4 dimensions, it just looks like, connectivity. We have all-to-all connectivity, so we can just simulate that by moving the atoms. So we have, a certain ordering of moving those atoms to the interaction zone to simulate the 4 dimensions. Yeah. And so in general, the code parameters look like this: 6 times d squared 6, and d is the distance. But the beauty is that it has very low logical error rate. And it has a nice high rate as well. So just to compare it, some of you I spoke with earlier, you were asking about the bivariate bicycle codes, for example. There's also the rotated surface codes. There's also some codes called SHIPs from Photonic, which is also one of our partners. And here, when we look at the performance of the beryllium codes, this family of codes, I've plotted a few different ones here, where we have the physical error probability and then the logical error probability. This is using a decoder called BPOSD, and a standard circuit level noise model. But you can see that, right around 10 to the minus 3, we have around a 10 to the minus 6 logical error rate. So you're gaining 3 orders of magnitude by using quantum error correction, a reduction in 3 orders of magnitude for quantum error correction here. So when we take this code, for example, the 9668 instance of this code, so 6 logical qubits, 96 physical qubits, we can look at the error rate per logical qubit, so divide by 6, and you get something that's better, better than 10 to the minus 6, 4 times 10 to the minus 7. The logical error rate at 10 to the minus 3 is around 10 to the minus 6, and it has a high pseudo threshold of 1%. If we compare that to the rotated surface code and the bivariate bicycle code, for example, these bivariate bicycle codes have been most recently looked at by IBM, then you can see we have a better per logical qubit error rate, and we have a better logical error rate at 10 to the minus 3, and we have a better threshold. So these beryllium codes, these 4D geometric codes that we have here are very, very competitive with other quantum LDPC codes that have been studied recently. Now, the other thing we look at then is to take these codes and we look at what would be required to get 100 logical qubits, 1,000 logical qubits, right? And so this code also has a family, right? We can take the 9668. That's a nice code for around 50 logical qubits. But as we go up to larger 100 logical qubits or 1,000 logical qubits, we can in fact take a larger instance of the code where we have distance 15, and now 6 logicals per 270 physicals. But that's still a nice low number, right? That's still a nice rate where we have 75 physicals per logical. As compared to the service code, you have 450 physicals per logical for a similar logical error rate. So we can take that. So you're looking at a couple thousand qubit system for 100 logical qubits. Less than 100,000 qubit system for 1,000 logical. So that's a huge change compared to what we used to think would be required to get out to, say, 1,000 logical qubits. So we're pretty pleased with that construction. I want to mention one other thing. Like, one way to get to scale, of course, we have to push up from the hardware side. We have to improve the hardware, get more logical qubits, more compute. But naturally, in a computer science department and a theory institute, one should mention quantum algorithms. Going back to my roots, as Christian mentioned, right? Algorithms, time and time again. I mean, I'm sure you all know this, but I thought this plot is quite nice. I mean, algorithms tend to win, right? They outpace hardware. If you have a new algorithm, it can be a game changer. And so, here, this is just a number of different algorithms where all of a sudden, right, what's the relative performance improvement to say the performance improvement of hardware, right? I mean, just huge improvements can come from algorithms that far outpace, for example, here, this is the hardware improvement over these years, and this is the relative performance improvement to that hardware improvement. So algorithms can have huge step changes in the ability to drive computation, ability to do computation. We need both. I'm not saying we only need algorithms. We have to continue on our hardware improvements as well. But if we pair it with algorithm improvements, the possibility for commercial value coming from quantum computing is just that much sooner. And this is where I think the field is really accelerating right now, because we are pushing at it from all directions, and that's huge. Just to mention a few papers along these lines that have excited me in the last year. Craig Gidney, he's speaking here tomorrow. So awesome, right? So awesome what he's done here, where he took the factoring algorithm. It's been known for a long time, right? 30 years. And he showed that he can now reduce to something that, a 20x reduction in qubit count required. So that's huge. That's a huge improvement. It really relaxes, makes it easier to get there. And it's a 100x reduction in Toffoli count. On the chemistry side, I put a paper in the middle. Guanghao Lo and his collaborators from Google and other places. Guanghao worked with us at Microsoft for a while. Chemistry algorithms here, they're able to show that they can get anywhere from a 4 to 195x reduction in gate costs, right? So again, a huge improvement in what the cost is to perform chemistry on a quantum computer. And then finally, I mentioned something recently that came out on using agents for algorithmic discovery. And in this work, very, very recently, just, last week, what they're able to show is they can actually find, using agents, they don't tell the agents about existing quantum algorithms, but they feed these agents some different circuit constructions and constraints, and it actually rederives very optimized algorithms for the quantum Fourier transform, Grover's algorithms, CHSH games. So that's pretty interesting too. Like, what else net new can it produce? It found the ones we know, but what else can we produce there from using AI? So I think there's a huge opportunity also to blend this type of thinking, with this type of work to drive down the cost of quantum algorithms, so that scale comes from squeezing on both ends. So with that, I want to just close and just say, there's kind of 3 takeaways for all of you today. The first, I see quantum computing as augmenting our AI era. One way is with new data for training, but maybe that's not the only way. The second is we need really good logical qubits. And the third, we need to squeeze from both sides to unlock scale. Continue to drive improvements on the hardware, get more logical qubits, more operations. But algorithms really help, right? If we can drive step changes in the cost of algorithms, what looks like what we call small or medium-sized quantum computers could just make a huge difference in industrially valuable applications. So with that, I will close, and thank you.
Okay, we eventually have to get out of here, but we have time for a few questions. So, questions? No question? Okay.
Hey, great talk. John Kubitowicz. Listen, I'm curious about the complexity of building codes that are easy to operate on, so that you don't, so that you can actually take encoded state and do all of your operations without changing the state. Obviously, the codes you're working on have that property, it seems, but how much work did it take to get that?
Yeah, it's such a good point. Finding these logical operations and then proving that they're universal and complete, And then making sure you can synthesize them is a series of efforts, let me say. We knew the logic, I would say Dave Asen and Matt Hastings, they wrote down what the logical operations for Beryllium should be and that family of codes should be, 2 or 3 years ago. But it took a good year, Vadim Klushnikov and others on the team, it really took a good year to prove that those were complete. And then now I think, there's been significant improvement, especially Vadim's work and others, on improving synthesis, right? How do you, and I have a set of slides on that as well, showing how many of these primitive beryllium operations are needed to do, like a multi-control poly, et cetera. So there's been a huge set of improvements there. The good news is it's efficient, but it is something to think about. And I think it's a really interesting question, right? How in the software stack, should we start thinking about algorithms directly? If you know you're going to use a given code, right? Should you think about these logical primitives directly as your primitives? How do we expose that the right way? Is it hardware optimized libraries that take advantage of these primitives or otherwise? Because right now, a lot of cases, quantum algorithms and quantum algorithm designers, they think in call it Clifford plus T instruction set. And that's not the instruction set that we have at our fingertips for these codes. And so there is a lot of work to really optimize that part, and how helpful it is it to expose those logical primitives directly? I think is an open question. But indeed, the synthesis algorithms are some beautiful mathematics. But now we have quite a few implementations there that work quite well, very well, efficient to find those.
So as a follow-on, maybe I turned this off, I don't know. So it seems like thinking in terms of non-Clifford operations is not something you worry as much about then. How do I get T's and then separating into Clifford T's? Or?
Yeah, we do. There's a whole new line of work really looking at how to layer the quantum algorithms and how to handle T's or other non-Cliffords. There's a lot of work, I think, tomorrow some folks here will talk about it as well, right? Everything from cultivation to distillation to... There's a lot of optimization for the given platform there. I think we are going to squeeze a lot out of those opportunities, kind of optimizing those things, and also really optimizing it for the algorithm itself that we're trying to run. Right? In the early days, we don't have unlimited qubits, unlimited operations, unlimited. Right? We really do need to squeeze everything out of every layer, and there's a huge amount of opportunity there. We do still think about the rotations, right? I think it's really critical we understand maybe there's a better way. At the physical hardware, you get an arbitrary rotation at 3, 4 nines, maybe even in some cases, if it's a Z rotation, you get it almost like basically perfect. But then in the error correction world, we say, hey, now you have to, you only get a T or you only get a CCZ, and you have to synthesize all the rotations you were using. That's a huge penalty. And so we need to continue to compress that. I think there's improvements there, but I think there's a lot more room there that we can take advantage of. Yeah. Really important questions. Yeah.
Thank you so much for the very nice talk. So I guess there are a couple of instances of you have the hardware's constraints, and you kind of optimize the codes to see how far you can push the codes. So I'm a hardware researcher. So what I'm wondering is, could you, for instance, take the application and the code you want to run as a starting point, and then define figures of merit for the hardware? For example, for superconducting circuits, you could engineer all-to-all connectivity, but it comes with trade-offs. So what is it possible to define figures of merit such that we could focus on hardware more on, let's say, 2-qubit gate fidelities or connectivities? Like, what should we prioritize?
Yeah, absolutely. So I think it's very important. It's something we do, for example, as we co-design this machine with Atom Computing, we do exactly that. So some of the things some ways we think about it is, at some level you have some hardware, I'll call it a hardware spec sheet, right? You as hardware designer and hardware developer, you have a set of specs that you're building towards, and here they are. We can take that spec sheet, and how I think about it is building out a feasibility region, right? For a code or maybe a whole set of codes, right? We then look in neighborhoods of that spec sheet to see, hey, what's the best thing to go push on next for the hardware, right? For you as hardware designer, I want to be prescriptive and predictive for you to say, hey, if you move this by this much, you're going to be in this much better region of logical error rate, or you're going to unlock, your cycle time is going to be reduced by, 50%, or making something up there, but that's the idea. And so that's what we do, is we try to take we do a coarse grain model of the hardware and the parameters of the hardware, the constraints of the hardware first, just to get us into kind of neighborhoods. And then we refine and do more and more fine-grained models of the hardware. And what we do is we take where the hardware's at, where the hardware will be, model that, and then model, kind of perturb each of those parameters. And so we perturb in many directions and then work to identify kind of, hey, here's an interesting feasibility range, and now you as hardware designer, you tell me which one is hardest, or which one's easiest, okay? And then let's go in that direction. So I think of it like visually in my brain, it's a lot like a gradient descent or something. I want to help hardware move in the, the nicest direction, easiest direction. So that's exactly what we do as we work, for example, with Atom and also with Quantinuum. And we push to say, hey, this error rate is actually the problem. And you need to reduce it by this much. And then all of this will get that much better. And we actually are precise on that, right? By this much in error rate, yeah.
Thanks.
Okay, let's thank Krysta again.
Thank you.